My name is Elektra Wagenrath, and I am involved with the development of the OLSR daemon. Um, my talk will handle internals of OLSR daemon by olsr.org. I hope you're interested in so much internal stuff and where the development is currently turning to. I've taken a shot of GraphViz of the Berlin mesh as the background of that slideshow. Hope you can see it. Well, olsr.org started as a master thesis of Andreas Tönnissen, a student at Uppsala University. He implemented the RFC 3626 OLSR that was issued by the INRIA Research and Development Organization in France. Our work is currently based on the primary work that Andreas Tönnissen did, but we made lots and lots of changes. We kicked many stuff out of the OLSR daemon that was in the RFC. You still can enable compatibility to the old RFC, but I think there is no reason to choose it. Well, this lecture is not so much of the kind I'm going to introduce into mesh networking in general, just a few basic information. The idea is to have a ubiquitous network that is an infrastructure made by the people that want to consume and use the network. The idea is to use the 802.11 ad hoc mode, the mode where the cards can directly speak to each other and there's no hierarchy. If routing is applied, we can potentially cover large areas because every node acts as a relay and improves the range. I think this will be clear with the next slides. What we want to do is not possible in managed mode. At least it is not possible in managed mode if you only have one interface in your mesh box. I have to admit that in the Berlin mesh, we are now using mesh routers that run links in infrastructure modes because we have several issues with ad hoc mode. The major issue is that drivers are implemented very sloppily because everybody buys cards when at least the infrastructure mode works to some degree. And many manufacturers, firmwares fail miserably in ad hoc mode. And of course, if you want to have a high bandwidth backbone infrastructure, meshing is not the ideal solution for it because if you only have one interface with every repeating process, the available bandwidth goes down because you have to repeat it all the time. In fact, if you use an access point not just as a resource for connecting to the World Wide Web or to a file server that is connected via the Ethernet to the access point, you have significant loss in speed if clients of the access point speak to each other. On that slide, if A and B communicate, well, the access point is quite fortunate, located in the middle, so it can extend the range of those wireless cards. Imagine the range of each card is 300 meters, and after 300 meters, in the middle between A and B, there is an access point. So there's a distance of 300 meters from A to the access point and B to the access point. They can speak to each other, which would not be possible otherwise. But imagine you have two laptops on the same table and you want to share some files. And the distance between D and B, imagine they are on the same table. The distance is 1 meter, but the distance to the access points is 300 meters. Well, you can be lucky if you have 20 kilobytes per second, especially here on the Congress. Compared to that, if you switch to ad hoc mode, you have the full speed, what your cards can have. C is out of the range of the access point. It would be in range of D or B, but they cannot speak to each other because in infrastructure mode, C needs contact to the access point. It's not necessary for the ad hoc mode, and I hope I stressed that out successfully. So in 802.11 ad hoc mode, the nodes can talk directly. This is decentralized, better scalable if the driver works, if the cards work. We have some really bad experience with that. And routing is applied because, well, in that slide, D is out of the range of A, so if B doesn't route, well, they cannot speak to each other, but we're here, or I'm here to talk about routing and mesh networks. Well, what we do, or what OLSR does, it is basically a proactive link state routing protocol. That means every node maintains a database of routes of every other node in the mesh. Here is how this routing table is generated. In the early beginning, imagine you just started the OLSR daemon on node A and B, C, and D. A starts issuing hello messages, which are heard by B. B is issuing hello messages, which are heard by A. So A and B learn that they exist and that they have a link to each other, which is symmetric because they can speak in both directions. Once the nodes learned about the situation or the topology of their neighborhood, they start flooding the mesh with topology information. Well, A says, I can see B, B says, I see A, C, D, and so on. Well, basically the basic proactive routing protocol, it just floods those topology information regardless if somebody has already heard it or not, all over the whole mesh. I think there's not much to say to this slide. Okay, this is the path of a topology control message and the repeated transmission of it. Of course, if you have a mesh with many nodes that have many neighbors, there's a lot of redundancy in this. Everybody starts repeating topology control messages and they get repeated several times. Of course, this consumes some bandwidth, and the academic approach of the research in ad hoc routing is the academics, they think first about optimizing the bandwidth consumption, and we will further on see how OLSR was intended to solve this problem and what we learned, what it isn't. Well, with the gained topology control information that is collected from each and every node, there is a table maintained, where everybody knows, okay, there's a link between C and A, via B, and so on, and so every node can calculate a routing table how every node in the mesh could be connected to. Usually these routing protocols, they search for the shortest path to route the package. So now, finally, we come from the generic proactive routing protocol to OLSR. It is a RFC draft, like I said before, 3626, issued by INRIA France. It's proactive using the Dijkstra algorithm that I just described. The communication works with UDP packages. They are broadcasted. Multiple messages can be contained in one UDP packet, and the messages are discarded if the validity time is exceeded and the validity time is told in the UDP package. Basically, what the O in OLSR stands for is those new ideas that were meant to improve this proactive routing approach. The integration of hysteresis and so-called multi-point relays. Let's handle the multi-point relays first. You see, there is a node in the middle, and it has several neighbors. And the idea of multi-point relays is to reduce the redundancy of repeated topology control messages. So a node decides it only uses several neighbors, not all, only a subset of neighbors, and tells the neighbors to forward its topology control messages. And others that are not told to be a multi-point relay, they don't forward hello message, topology control messages. And it learns this from hello messages. Well, our experience, we first tested OLSR on the Wizard of Oz at 2003. It doesn't work. We switched this feature off. It was one of the major features that were introduced in OLSR. We found several issues in this new idea of proactive routing. It adds a new and, in my opinion, unnecessary message class and is telling who is a multi-point relay or not. It's still like the previous routing protocol that we tested, like it was mobile mesh. It optimizes routes for the lowest hop count. It tends to find the shortest path, which is not fortunate, and I will explain this later on. The worst thing that made our work completely or mostly useless with OLSR in the beginning was that it has a so-called hysteresis. If 3 hello packages from a neighbor are lost, then the neighbor is kicked out of the routing table. That's very unfortunate if this node that was kicked was a multi-point relay before. That was supposed to forward your topology control messages. So the node ended up without having a multi-point relay and without having a link to a neighbor. This happens binary, and yeah, it's just on and off. I have a neighbor, I don't have a neighbor. And what we were seeing and experiencing was we had a routing table that was very long. It broke down, it rebuilt it, it broke down, it rebuilt it all the time. This nice idea, or in theory, on the first sight, nice idea of multi-point relays, it reduces topology information redundancy. Well, it's what it was meant for, to reduce the redundancy and save overhead. But it also reduced the stability in the network, because once you have traffic in your mesh network, you have collisions. And so some packages don't come through, and so you're quite happy if you have some redundancy. And last but not least, every node floods the whole network with topology control messages. Imagine you have a network with 200 nodes, and you say every 5 seconds, every node broadcasts its topology control messages. So every few milliseconds, there is another flood issued by some random node in the network. And what I disliked most was that OLSR breaks the KISS attitude. Yeah, the routing table broke down all the time. It seemed to prefer routes with the shortest path, the lowest possible bandwidth, and no stability. And routing loops occurred more often than not. So the lessons that we learned on Wizard of Oz 2003 was a mesh is a boiling kettle with interference and collisions, especially the mesh that we used because we had only one channel. We were transmitting on channel 10, so everybody is using the same resource, and there are lots of collisions. There are hidden nodes, exposed nodes. And if you need 10 dB signal-to-noise ratio to have a successful transmission with 2 megabit, well, a node that is far out of range still adds some 2 or 3 dBs noise to the noise floor you already have. So it cuts down the signal-to-noise ratio even if it is completely out of range. What we further learned, theoretical solutions in simulations are unlikely to work in real-life scenarios. I hope that those guys at universities, I'm sorry to, to insult you, should go away from their network simulators and start real-life tests. And the optimizations, well, I think first we should make it work, then we should make it stable, and later we should worry about routing the whole universe in one subnet. Proactive routing algorithms depend on synchronized information, and therefore, because we have lots of interference and collisions, transmissions must be redundant. So new message types introduce a new source of failure and new information that has to be synchronized, otherwise it will cause confusion, and so it causes new headaches. What we did after Wizard of Oz was we disabled hysteresis at first. We disabled the multi-point relay section in the configuration file, and we started working on implementing a route calculation depending on packet loss. I'll explain this further. And the last thing that is new in the CVS version and in the upcoming 0410 release is a link quality fisheye feature that will replace the multi-point relay attempt of INRIA. OLSR, like I said before, it minimizes hop count in routes, hence it favors longer and lossier links. So the default OLSR daemon will choose a route A, B, C. But between B and C, there's 30% packet loss. There's an alternative route with very low packet loss, but most routing protocols like OLSR, they would not choose such a route. They will always blindly choose a route with the shortest path, and combined with the hysteresis, it will very soon drop the link to B and forget about it and start rethinking about the network topology. We did some research with other metric ideas. We tried to measure the latency of round of packet transmissions, but this is a really hard task. We didn't get good results with it. Another idea would be to measure the throughput of a link, but I have no idea how to measure throughput without issuing traffic, and that would, of course, generate a lot of overhead. Well, the protocol is working with broadcasts on the UDP traffic. So what we did was we implemented an ETX-like solution. ETX was a paper issued by somebody at MIT, which suggested that every node should send some UDP packages, and the other nodes, they expect to receive those UDP packages, and by the number of packages that are expected divided by the, or computed the number of packages that are lost, we calculate a quality of the link, a likelihood that a package has to be retransmitted. We named it LQ. So here, A transmits data to B, and the likelihood that the packages come through is 90%, and the acknowledgements that come back from B have a likelihood of 70%. And we calculate the ETX value, which is just, I missed the English word for it, the reverse. Der Umkehrbruch. Okay, and this value here in the example with 1.59, it's just added as a metric when calculating the routing table. And the result, we introduced the ETX in 048 of OLSR, and we had some bugs in the first implementation. But even with 048 and now with 049, many people successfully have built mesh networks all over the world. There are mesh networks here in Berlin. We have 180 nodes, I think, at the moment running. In Leipzig, they have 60. In Rostock, I heard about 100 nodes, and they are all operating in Rostock in ad hoc mode, all based on WRT54 from Linksys with open WRT software, and they're really satisfied with it. Still, we had some issues with 049 under high traffic load. As links saturate, we faced routing loops, and the new release 0410 will address these issues. I learned that networks that are not saturating their Wi-Fi links are not affected by these routing loops issues. We have a killer feature in Berlin, download from dev0, which saturates the bandwidth, and are really funny effects that you can view when you watch it. We have 2 mesh clouds at the moment in Berlin that are independent. There's one in Hohenschönhausen and Weißensee, and one here in the center of the town. When some freaks interconnected both mesh networks, we finally saw that we now pushed OLSR to the limit. We always knew that there is an extent to what OLSR can work, and we wanted to find out when it actually crashes, when actually the weakest CPUs start glowing and cannot handle to recalculate the routing tables all the time. And with more than 200 nodes, we faced this problem. So the older versions of WRT54 with only 120 megahertz CPUs, they couldn't handle that CPU load anymore. They were not able to recalculate and started sending false messages and so on and so on. So the problem that we are addressing now with the new and upcoming release is the problem of routing loops. It's a basic problem which can always occur in a proactive routing protocol. Because every node maintains a routing table, there are problems if the routing tables are not in sync. Well, in such a big mesh like we have here now, the routing tables in fact are never in sync. Never, never, never. But usually this is not a problem. If you have a link with 10 hops, a node on one end of the mesh may have the illusion that it exactly knows the exact path the package would go when it is sending payload to a node 10 hops away. But this is very likely an illusion. But it doesn't harm the communication. A node somewhere in the mesh only needs to know which neighbors are the right choice to hand the packages over to get into the right direction. Nodes that are more far away from the node issuing the traffic and nearer to the node that is intended to receive the traffic, they know better about the routes because they have information that is more in a timely manner, that's more up to date. So here is an example of what we saw when we looked into OLSR daemon and what it was doing in the nodes. Everything is fine here except that D has a different idea about the best path to E. There was formerly a link existing between B and E, but B and E just learned that this link is not usable anymore. D still has a link, the others know about it. But D thinks the best path to send packages to E is sending them to B. So the package that comes from A or is forwarded by A from somewhere goes to B, C, D, B, and then we have the loop. And the packages, they have a time to live, which is a good thing, because without a time to live stamp, some packages would run around in our network for ages until we cut the power. So it is looping very fast in a few milliseconds. It is looped several times, the time to live is exceeded, and the node that drops the packages sends a message back, hey, time to live exceeded, no route to host. The problem occurs all the time when the routing tables are not in sync. And my thesis is that it only occurs amongst a few neighborish nodes, a few adjacent nodes, because it's very unlikely that the packages is running in a routing loop that goes from Hohenschönhausen to Mitte and then back to Weißensee. That's very unlikely. So it's more likely it happens between only a few nodes. It can very well happen that B thinks, hey, the best way is to send it to C, and C thinks, hey, the best way is sending it to B. The nodes are not intelligent enough to just say, oops, I just had this packet. So what we learned about the routing loop issue is it occurs when topology information is not in sync. Loops happen among adjacent nodes. Interference causes topology information loss. Payload traffic causes interference and therefore topology information loss. So topology information must be redundant and sent more often than hello messages to provide information timely. Imagine if you send topology control messages every second and hello messages every 5 seconds, chances are you have sent that information that something changed 5 times before something changes again. That was not correct, forgive. And the technology of multi-point relays, which should reduce the protocol overhead, it doesn't help here and with these issues. The only thing that helps is send topology control information very frequently, very often. But of course, with multi-point relays, this is not possible because the mesh would just suffer from so much topology control messages that are issued from every node all the time. So we started reusing idea which we already used before, which was introduced in mobile mesh. It's called fisheye routing. We call it link quality fisheye. These topology control messages, they have a time to live stamp. And we just, with a simple hack, we manipulate the time to live stamp. We send packages with a time to live of 1 very often. With a time to live 2 quite often. With a time to live of 3 often. And with a time to live of 255, which is now the default in the previous releases, every now and then. At the moment, every 13th package is a topology control message that is sent all over the whole mesh, flooding the whole mesh. The result is that the neighbors in the green circle, if we issue topology control messages every half second or second, they are updated every half second. At the moment, with the set that we have at the moment, these neighbors, they get it every 2.2 seconds. In the blue ring, they get it every 4 seconds. And in 255, they get it every 6.5 seconds. I'm not really sure about it. In the effect, so distant nodes have a hazy view about the topology in the network, which is sufficient. They don't have to know precisely about the structure. They only have to know, yes, out there are some nodes, and this is their IP, they exist, and they have a relation to each other. That is sufficient. But information about the topology in a local area must be very precise, otherwise we have those routing loops. We can of course not grant that still the problem of routing loops can occur, but I think with the new release, which is currently untested, and I hope people start using it really soon, you can get it from the CVS part. It's for Linux, it's ready to release, but we're waiting for feedback from the people using it on BSD, macOS X, and Windows before we issue the 0.4.10 release. Yeah, 0.4.10. I hoped we would have released it until the 23rd of December, but it's still not released yet. But like I said, you can already use it for Linux. It should work really well. We're already testing it here. We hope that we get feedback from the other OSs. Already, if you still use 0.4.9, it's reasonably stable for smaller meshes. If you only stick to ad hoc mode, it works with 100 nodes quite well. If you mix it with multiple interfaces, and if you have infrastructure link, it works up to 200 nodes. Yeah, there's some new features like a plugin interface. We have a web-based tool for monitoring the state of the mesh. And we have the link quality fisheye algorithm. So I hope I didn't bore you. Thank you for your attention. Pardon?
Country coverage, wide areas, not on a local base.
Please use a microphone.
Are there any projects regarding to use this technique in a wide area network, not only on ad hoc mode systems, to adapt the protocols like the fisheye mode or stuff like this?
The technology that we are developing is intended to be used in a subnetwork. You can build a subnetwork in a quarter of a town, in a district of a town. You can use it mobile with friends on your laptop, on your PDA. It's not intended to route a whole country or a huge city. It's not possible to do it. There's clearly a limit to what a proactive routing protocol can scale. There are some theories of people that work on reactive routing protocols that only generate routes on demand, that don't have to maintain routing tables all the time. They're very optimistic. They say their subnetworks and their mesh routing protocols could scale to 10,000s of nodes. But I have my serious doubts that they can achieve it, especially because all the failures that we have seen in our real-life tests are still there. They're still happy if they find the shortest path, and that is clearly not enough to have a mesh that works.
Sorry, did you think about ant-like routing schemes? Like I heard the routing scheme used by ants.
By ants?
Ants, yeah, like ants, if they try to find something.
I have to admit no, I cannot say anything
They just
about
go
it.
out somewhere and leave some chemical substances which evaporate eventually, and the more ants they take that way, the stronger the substance track will get.
Mm-hmm.
And people were thinking about emulating something like this for routing.
Well, I have to admit I didn't look into that. I still stick to the proactive approach. Of course, it is a good idea to look into the nature, and there are many algorithms that you can see in nature and reuse. This is, of course, a good thing, yes. but I cannot say anything about it. And of course, there's several approaches to mesh routing. It's not only the proactive or the reactive approach. If you check out the English Wikipedia page about mesh networking, you'll find many, many, many papers and many, many different approaches. Amongst these are graphical routing protocols, where you have geodetic data and route according to geodetic data. Other protocols are clusterized, are working with hierarchical ideas. And then some people at the university here in Berlin are working on it, but they're still, as far as I know, they're not addressing things like interference, like finding really good routes. I think they're quite happy if it works to some extent.
I noticed you had like 1 second updates or something like that, and it seemed like very short intervals. Is it because you want to allow nodes moving around, changing positions, people walking with the laptops, or is it because you want to detect nodes that goes offline? You want to detect that very fast?
In fact, at the moment we are migrating from relatively long topology control intervals of, I think, about 5 seconds or 4 seconds to half a second or 1 second. 5 seconds is a lot of stress for the mesh because we have so many nodes. But in the future, when we use that fisheye feature, those topology control messages, like I said before, they don't travel far, so we can issue them very frequently. So we can keep adjacent neighborish nodes up to date with routing information, with information about the quality of their links. And this should, I'm very, very convinced that this will give the project and the software that we provide the next bigger boost. The last boost or biggest improvement was ETX, and although this fisheye routing thing is a very simple hack, I'm very convinced that it will be a big improvement and move OLSR daemon to the next step. I can tell you that we are now in the development dropping the backward compatibility and those features that allow to configure OLSR daemon to be backward compatible with the old NVIDIA drafts. We will completely drop it in the 0.5 release and further. 0.4 will only contain bug fixes in the future, and I think it will, it's deprecated and it will not go so much further. 0.4.10 again has a new feature and is still on the bleeding edge of the development, but with the beginning of the next year, all this development will only happen in the 0.5 release.
If you have a wireless network with multiple uplinks or peering partners, how good is load balancing possible?
Load balancing, no, we don't have something like that. At the moment, all that OLSR does is find the next gateway and use it. And there's still an unresolved issue if you are between 2 internet gateways and you have a SSH connection, perhaps. It could happen that the protocol designs, okay, now I choose the other gateway, now I choose the other gateway, and this is of course annoying because we usually do network address translating on the gateways, and your SSH connection will break down. This is of course an issue. You can, with some handwork, you can manipulate which gateway you in fact choose, but this is handwork. There's no automated solution for it at the moment. This is still an unresolved issue. We're still working with one interface, although OLSR daemon can handle multiple interfaces. In Berlin, many people are using OLSR daemon on their machines. They have several interfaces, wireless interfaces, Ethernet interfaces. They enable OLSR to send hello messages on all interfaces and let OLSR do all the design of their network. which is quite tempting. And I like it. It's not like intended, but it works. And we can boost the performance of the mesh if we start using more devices that have several wireless interfaces on different channels, so we don't have so much interference. That will give another big performance boost. I expect commercial companies that are going to develop mesh solutions to go more and more into this multiple interface ad hoc part of the mesh thing. We can expect it real soon. At the moment, the solutions that I heard about from Cisco, perhaps they have a very expensive mesh router that costs $5,000. It has 2 wireless interfaces, but one is just in use to provide infrastructure network to the clients, and 1 ad hoc interface to provide a backbone structure to connect to the backbone. In future, there will be devices that have several interfaces working all in ad hoc mode, of course. This will be the next step, but we are, well, my intention is to have a community network that is cheap and has range covering large areas, and if we start moving to have several wireless interfaces in each device, this is of course a cost factor. It will give enormous performance. Yeah, but it will cost. I expect for the community this not to happen so soon, but it will happen in the commercial development of mesh networks. Yes, I heard about it. There's one company, and they have really impressive papers about, hey, we solved the mesh issue. We have now several interfaces. Well, yeah, sure.
Can you say something about how this routing algorithm reacts to very fast-moving nodes?
The mesh networks that we use, they are mostly static. If I'm frank, I have some doubts in my work because I'm afraid that people in the military will use it. It may be used for surveillance, and of course they may benefit from our work, and I know that they have a close look at what we do. My idea is not to develop something that couldn't be used in a tank or robot-driven bomb on a battlefield that is moving rapidly around, or somebody riding on a motorcycle and using a mesh network. That's not my vision, and the work that I do is not pointing into that direction. Other people, of course, work into that direction.
Okay, one question. I realize you have link equality information now factored in by packet loss, more or less. However, that's not the only consideration. Obviously, we can have very little packet loss in a low bandwidth link, while some nodes which are closer by, while they might have some packet loss, the link might still provide more throughput. It's probably hardware dependent, but are there any developments where you would factor in signal noise ratios or the effective link speed into the protocol?
Yeah, well, we thought about it, but what we do is providing a help for community networks, and community networks have a heterogeneous hardware structure, and so the lowest consensus that we could use amongst all those different hardware with all those different drivers was to implement ETX. That was and is, in my opinion, a good step forward, but of course it is not perfect. The perfect solution would be to have a hardware that does all this in firmware. That does, if a company starts developing something like this, and create their own standard, or hopefully an open standard. They can measure signal to noise ratio, they can measure the throughput, and they can measure everything. But it's impossible to do this with that solution that we have here, where we have just a user space program that runs on several different operating systems with different cards. But of course, if there is a lot of money and that could be spent in development and designing hardware, this can and will be done, yes. But this is not the work of the community project that we have here.
Okay, could this be done through plugins, for example, hardware-specific plugins?
Sure, there is a plugin interface that it could be done. If you have a homogeneous hardware infrastructure, then a lot of things are possible. Bruno Randolph, he implemented mobile mesh for the 4G access cube, which is now no longer available, and he implemented measuring signal to noise ratio because he had a homogeneous hardware and he could use this as a metric. But he learned that the signal to noise ratio is, you can have a link with a very good signal to noise ratio and no bandwidth at all. Because if there's a lot of interference from adjacent nodes, then this doesn't help much. So ETX is not the one and only metric forever, but it's a good way at the step of evolution where we are now, and in the situation that we have to deal with different heterogeneous hardware platforms.
Hi, Electra. You've spoken about 0.4.10. I'm just wondering what's a bit further in your roadmap and your ideas for the protocol?
Well, with 0.5, we're going to kick out all those legacy stuff that came from the RFC. There's no need to maintain all those code lines that were meant to provide hysteresis and all this other stuff that we switched off long ago. And we are going to head further to new developments. The first thing is, yes, multiple interfaces, coordinating transmissions on different channels, different frequencies, avoiding collisions. This is on my roadmap. And for the Berlin mesh, we will see how far we can scale the proactive protocol in Berlin and then start switching to subnetworks. We can no longer handle everything in one subnet. This is, of course, fascinating. We will go to the limit, and then we'll switch to subnetworks. And as the network is growing at a very high pace, we will have to do that switch really soon. I expect it in spring. More questions?
I'd like to know what kind of latency you can expect in such a network. If you have to route a package across maybe 10 nodes, isn't it a huge problem, the latency?
I assume you did a ping before on a machine with a wireless link, and as the wireless link got weaker, you saw the increasing of the round trip time. The reason is not that the packages take longer time to travel because the signal to noise ratio is worse. The cards internally, they do retransmissions. And so the increase comes from the necessity to retransmit packages until they come successfully through. If you have reasonable links, then the latency is not so high. If you measure round trip time with ICMP to the first node, you have 3 milliseconds. If the link from the first node to the second node is good, the same quality, you have 6 milliseconds round trip time to the next node, and so on and so on. So as long as the links work, even if you have 10 hops and the nodes are not completely saturated and running out of CPU power. The latency is maybe 40 milliseconds. I was developing and working on voice over IP solutions in Bangladesh, where we had a VSAT link for voice over IP. Everybody says, yeah, well, voice over IP is not usable anymore if you have more than 100 milliseconds latency, but I learned that you can live with 700 or 800 milliseconds. But in a mesh network itself, yeah, you will have 40 milliseconds, maybe 50 or 60. And if it gets worse, then you have so much packet loss that the voice over IP starts sounding really odd. Voice over IP is on the agenda as well for the next year. So doing phone calls within the mesh and have voice over IP gateways and coordinating them. This is, of course, a thing that we are going to address this year. Okay, there's no limit. This is the last session. And I have enough to drink.
Do you change the packet size in any kind, or 1500 all the time?
No. No. If you set up a wireless interface for a mesh network, there are a few basic settings that you have to choose. Amongst these, you have to use fragmentation, small packet size, and you have, of course, to use the request to send, clear to send mechanism, and you have to use very conservative values. Otherwise, it will not perform, because hidden nodes are the default in the mesh, because that's what mesh is meant for. And you have lots of interference, especially if you only use one channel. So it's a must.
I have a question about if you said that there's going to be lots of TC messages, and as far as I remember, there's basically the messages get combined, so a UDP packet becomes quite big actually. So if you send big packets all the time, very often to the neighboring nodes, only radius 1,
Well,
then the frequency also gets clocked, right, or not? Or did I understand something wrong?
Yeah, well, the fisheye extension, it's possible that we may have to change some things. The aggregation of messages, yes, it has to be checked again.
The other question is, like, what help is needed for developing?
Pardon?
What help is needed for developing?
Oh, well, if people that write nice code want to jump on the train, that would be lovely. I'm basically not a good coder, and most of the coding work, especially in ETX, was done by Thomas Lepatik, and he's at the moment very busy. So if more people are like to get involved with it, it would be lovely. Okay, well, I can close my laptop now. Thank you.